You ever wonder how some things just seem to explode? You know, like a viral video, or how a tiny investment can balloon into a fortune? Well, the secret behind all that is the math of exponential growth. And today, we are going to unlock its secret ingredient, the geometric sequence. Our mission is to figure out what these things are and how one single powerful formula can let us predict the future of any pattern that grows like this.
And by the time we're done here, you'll be able to nail down exactly what a geometric sequence is. You'll be able to spot its most important piece, the constant ratio. And you'll be able to use the general formula to make some pretty cool predictions. And look, this isn't just about acing a test. It's about really understanding the engine that drives everything from your savings account to the way ideas spread around the world.
So, here's our game plan. It's super simple. First, we're going to ask, what is a geometric sequence? Then, we'll get our hands on that powerful general formula, and finally, we'll roll up our sleeves and walk through a couple of examples to make sure it all makes perfect sense.
Okay, let's dive right into the big question, what is a geometric sequence, really? Well, the whole thing boils down to one simple but really powerful idea, and that's the constant ratio.
So, at its core, a geometric sequence is just a string of numbers that's all about multiplication. You start with one number, and then to get the next one, you just multiply it by the exact same value. And you just keep doing that over and over again. That special multiplier is the key to the whole thing, and we call it the constant ratio, or just R for short.
So how can you be sure you're actually looking at a geometric sequence? Well, think of this formula as your detective tool. To find that constant ratio R, all you have to do is pick any number in the sequence and divide it by the one that came right before it. If you get the same answer every single time, no matter which pair you choose, boom, you've got a geometric sequence on your hands.
Let's make this real. Imagine a virus spreading through a community. Day one person infects two friends. The very next day, each of those two friends goes on to infect two more people. You see what's happening? This pattern of multiplying is a perfect and, honestly, a kind of scary example of a geometric sequence in the real world.
Let's just track that growth for a second. On day 1, we've got 2 new cases. By day 2, that number doubles to 4. Day 3, it doubles again to 8, and by day 4, we're at 16. The pattern is crystal clear, right? Every single day, the number of new infections is being multiplied by 2. That gives us our sequence, 2, 4, 8, 16. And here's the proof. Let's pull out our detective tool. What's 4 divided by 2? It's 2. Okay, what about 8 divided by 4? Also 2. See? The ratio is constant. So for our flu example, that all-important constant ratio, R, is 2. Okay, now that we've totally nailed the constant ratio, we can get to the best part, the general formula. Think of this as a time machine. It's a tool that lets us jump way into the future of a sequence without having to calculate every single step to get there. And here it is. T sub n equals a times r to the power of n minus 1. Now, I know what you're thinking. It looks a little complicated at first. But trust me, this thing is like the master key for any geometric sequence you'll ever find. With this, we can find the 10th term, the 50th, even the 100th term in a snap. Let's quickly break down what each piece of that puzzle means. T sub n, that's just the term we're looking for. Easy enough. A is our starting point. It's always the very first number in the sequence. R is our good old friend, the constant ratio. And n is just the position of the term you're curious about. So if you want the 5th term, n is 5. Simple as that.
All right, enough with the theory. Let's make this stuff concrete. It's time to actually put the formula to work with a couple of quick examples. This is where it's really going to click.
Okay, let's take a look at this sequence here. 5, 10, 20, and it just keeps going. The first thing we need to do, the most important step, is to figure out what our constant ratio R is.
So let's just walk through it. Step 1, we grab the first 2 terms, which are 5 and 10. Step 2, we use our ratio formula, which means dividing the second term by the first. So step 3, we calculate 10 divided by 5, and we get our answer, 2. That's it. The constant ratio R for this sequence is 2.
Okay, for our second example, we're going to stick with that exact same sequence, 5, 10, 20. But this time, our mission is to build the special, unique general formula just for this sequence.
And this is where everything we've learned comes together. First, we identify our starting term, A, which is of course 5. Next, we need our constant ratio, R, which we already figured out is 2.
Now, all we have to do is plug those two numbers into the general formula blueprint, and that gives us our final answer. T sub n equals 5 times 2 to the power of n minus 1. And now, with this formula, we can find any term in the sequence we want. Okay, let's do a super quick recap of the most important takeaways from all of this, just to lock it all in.
So, what are the absolute must-knows? First, every geometric sequence has a constant ratio, r. It's its DNA. Second, you find that r with a simple division, any term divided by the one before it. Third, the first term is always called a. And finally, that master key that ties it all together is the general formula. T sub n equals a times r to the power of n minus 1.
So we'll wrap up with this thought. Getting a handle on geometric sequences isn't just about passing a math class. It's about understanding the powerhouse that is exponential growth. We saw it with a virus, but this pattern is absolutely everywhere. In finance, in technology, in nature. So I'll leave you with this question to think about. Where else in your world do you see patterns that grow this fast and this powerfully?